Hi friends, welcome back. Now let's get into the second type of scheduling algorithm under non-preemptive scheduling, the shortest job first. This is a non-preemptive scheduling algorithm which selects the process having the shortest CPU burst time as a next process under execution. So among all the processes which are in the ready list, it identifies how much time each process needs to complete its execution and then arranges them in ascending order as per the burst time, and then the smallest burst time process is allotted first, and then it continues like that. So to understand a better way, let's take up an example. Here we have four processes P1 through P8 having burst times 8, 4, 2, 1 respectively, and if you look at it, the shortest job here is P4 with 1 unit of time, and the next shortest job is P3 with 2 units of time, and next is P2 with 4 units of time, and finally P1 with 8 units of time. So that's how the processes are allocated: first P4, then P3, then P2, and then P1. And what is the advantage of doing this is the average waiting time. So look at P4 immediately starts working, therefore it doesn't wait, and P4 takes 1 unit of time, therefore the next process P3 has to wait for this 1 unit of time when the CPU is executing P4. So waiting time for P3 is 1 unit, the next process is P2, and P2 waits for process P4 and P3 to be completed by CPU, so that makes totally 3 units of time, and finally P1 gets its chance after P4, P3, P2 are executed, that is 1, 2 plus 4, that is after 7 units of time P1 gets its chance, so P1 has to wait for 7 units of time. In all there are 4 processes, therefore added them, divide by 4, that gives our average waiting time, that comes to 2.75. Now let's check up when we have these processes not coming at the same time but arriving at different times. So if this happens, then what will be the scenario? So at 0 time, when we begin our scheduling system, then at 0 time we had only P1 available, and which is having 8 as a burst time. Therefore the scheduler starts working with P1, and since this algorithm is non-preemptive, therefore after 1 unit of time P2 comes up, and even though its burst time is less than the remaining time of P1, it cannot stop P1 and allot P2 because it is non-preemptive. Therefore once P1 starts executing, then for 8 slots P1 continues to execute, and by the time P1 completes it, we have spent 8 units of time, so the timer has crossed 8 units, and in this 8 units of time P2 has arrived, P3 has arrived, P4 also has arrived, because now the clock is showing 8, and P1 has come at 1, P2 has come at 2, and P3 has come at 3. Therefore at 8 all 3 P2, P3, P4 are available, and then shortest job will check the burst time and then realizes this P4 is the smallest burst time, therefore the next job allotted is P4, and now we are left with P2 and P3, both are there in the ready list, and P2 requires 4 units, P3 requires 2 units, therefore P3 gets the chance, so 2 units of time is reserved for P3, and the next 4 units of time is reserved for P2. So that's how the things happen. Now if I look at the average waiting time, then P1 begins immediately when it was arriving. So the average waiting time for P1 is 0. Now if you look at P2, then P2 starts at instant 12. That means for level instance it was waiting. Then P3 begins at instant 10. That means it has to wait for 9 minus 2, that is 7 units of time, and then P4 is at 9 minus 3, that is 6 units of time. So that's something around average comes to 6. Now instead of non-preemptive, if it was preemptive, then we would have started at 0. There was only P1, so we start with P1. But after 1 unit of time, P2 arrives, and then we realize that P1 has done 1 unit of work, still 7 unit of work is available. P2 needs only 4 units, therefore P2 gets the chance. So 1 unit of time P2 is getting, and after 1 unit of time P3 comes in and it says I want only 2 units, whereas P2 wanted 3 more units and P1 wanted 7 more units. So 2, 3 and 7, so 2 happens to be the smallest, therefore now P3 gets its chance. Then at the third instant P4 also comes and it says 1 unit. So at that time P3 wanted 1 more unit, P2 wanted 3 more units, and P1 wanted 7 more units. So both are 1 1. So it can be either P3 continuing or we can give chance to P4. So assume that we have given chance to P4, so P4 completes its job, and then P3 1 more is required, P2 3 more required, and P1 7 more required. So P3 wins the race, so the remaining 1 is allocated for P3 next, and then P2 wanted 3 more and P1 wanted 7 more, so 3 is more than 7, so 3 units of P2 allocated, then 7 units of P1 is allocated. If we were working in non-preemptive, preemptive type of scheduling, in that case, if you look at it, the average waiting time would be for P1, it starts here, then not P1 working, no P1, no P1. So 1, 2, 3, 4, 5, 6, 7 units of time P1 is waiting, and P2 waits, it comes at unit 1, therefore this is not waiting. Then 1, 2, 3 units of time P2 is waiting, and P3 comes at 2, therefore P3 comes at 2, the immediately P3 is given a chance, therefore here it is not waiting, but 1 it is going to wait for 1 unit of time. And looking at P4, P4 has come at 3 and immediately it gets the chance, so it is not going to wait anymore. So total happens to be 11 by 4, that is the average is 3.75. and if you look at the average response time for this, P1 begins as soon as it arrives, so response time is 0 for that. P2 arrives at 1, immediately it gets response, so response time for P2 is 0. Then P3 at 2, so at 2 P3 comes and immediately it gets the slot, so its response time is 0. Then P4 is at 3, immediately it gets, so it's also 0. So the average response time for this particular situation is 0. That's a best way. The only thing is it has to be a preemptive thing, but usually shortest job first is a non-preemptive thing. So let's look at another example. This same example we had seen when we were looking at first come first serve, and if it was first come first serve, then 21 gets chance first, then 3 gets the chance, then 6 gets the chance, then 2, and if you look at it, then the first process there is no waiting time, but second process has to wait for 21, third one has to wait for 21 plus 3, that is 24, and the fourth process has to wait for 21 plus 3 plus 6, that is 30. So in all, average waiting time was 18.75 for this particular problem. But the same problem, if we apply shortest job first, then the shortest job is 2, so P4 comes first, then 3, that P2 comes next, then 6, then P3 comes next, and finally P1 comes. And if you look at it, the waiting time for P4 is 0, waiting time for P2 is 2, and waiting time for P3 is 2 plus 3 5, and waiting time for P1 is 2 plus 3 plus 6, that is 11. So the average comes to 4.5. Now let's look at some problems associated with this. So let's take another example. Here two processes P1 P2 arrive at the same time 0. The P1 has got a burst time of 10, P2 has got a burst time of 2. So once we begin our process, then at instant 0 there are two jobs waiting in the ready list, P1 and P2, and P2 needs 2 units of time, P1 needs 10 units of time. Therefore shortest job first scheduling says P2 should be given chance first, therefore P2 is given chance. And by the time P2 is run, 2 units have elapsed, and that time P3 has come in. After 2 units of time, P3 has arrived. So now on the ready queue, we have on the ready list we have P3 as P1. P3 needs 2 units, P1 needs 10 units, therefore P3 wins the race. So next 2 slots allotted to P3. So now we have elapsed 4 units of time, but at the third instant P4 joined our race, and at this, when we completed P3, P4 and P1 are in the race, and again P4 time is 2, P1's time is 10, therefore P4 wins the race. And by that time P5 also has come in, and it also needs 2 units, so that will win the race. So P5 gets 2 more slots, and if nothing comes later, then P1 gets 10 slots. But this whole situation is dynamic in nature, so P1 P2 we are talking about arrival time. Then maybe somewhere at 5 P6 may come in, that also say wanted 2 or 3 units of time. Then at 5 P5 has completed, at 8 and at 5 P6 has already arrived. That means 3 units of time required for P6, 10 units for P1, therefore P6 will get the chance for 3 more slots. Then P1 gets delayed. Then unfortunately for P1, in another process with burst time less than 10 comes in. So if this scenario continues, and each time one process completes its job, there is another process waiting in the list which has a burst time less than 10, then it will get the chance, and the next time another one comes in, and that will get the chance, and that way it may so happen that P1 keeps waiting forever. So it may get into something like an infinite loop, wait and wait and wait and wait. So that's what we call starvation. So let's look at some advantages and disadvantages of shortest job first scheduling. This one, as we have seen, it minimizes the average waiting time, definitely. It improves the throughput because the smaller jobs are taken first. Therefore, every now and then some jobs come out saying that I have completed, I have completed, I have completed. So if you keep looking at how many jobs are completed, so the count keeps increasing quite fast. Therefore, you will have a better throughput. Then it is ideal for batch systems. That means when one batch we have a set of processes. So before beginning this scheduling to this batch of processes, we know which process needs how much time. Therefore it will be easier for doing it. Disadvantage, yes, burst time must be known in advance, otherwise you cannot say which was shortest. Now you say 10 is the first job, I don't know what happens next. The next job may be 2 units, next job may be 200 units, don't know. Therefore it is very difficult to say what is the best job. Therefore all these burst time should be known in advance. That's why we call it a batch system. That's a disadvantage of working with this. If you don't know that, then as just discussed previously, it can cause starvation for a longer jobs. We have seen in the previous P1 keeps on waiting because new processes keep coming, because we are not working with a batch system. So if we don't work with a batch system, then we are not limiting our number of processes to one particular batch, and then once you limit to a batch, then you can arrange them in order and then start working with that. So definitely each process will get one schedule, and accordingly it will be definitely solved. It will be given CPU and it gets solved. But if we have a dynamic situation, as we just discussed few minutes back, then every time smaller jobs keep coming, then this big job which had come earlier keeps starving forever. So that's another major disadvantage we have with this, and definitely not suitable for interactive system, because interactive system is one when I press a mouse button, immediately I wish to see some reaction from the system, I need to see some changes on the screen and all that. But if the process for which my mouse is giving a signal, and if that process happens to be a very big one, then it keeps starving and that will never be addressed. So it is definitely not suitable for interactive systems. It is only suitable for batch systems and all that, and definitely it is hard to implement in general purpose operating systems. We can expect its complicated implementation and all only when we want a specific operating systems to be devised. But in case of general purpose operating systems, so definitely this is not well suited. So more details about what is general purpose operating system, what is specific purpose operating system, come in future sessions. So that's it about the. Now if you look at the performance of this type of scheduling, then CPU utilization is high if the jobs are known in advance. Throughput is definitely high, turnaround time is low, waiting time is minimal, response time is moderate, starvation possible. So that's it about the shortage job first scheduling algorithm. So please make sure to like, comment, share and subscribe to this channel. Thank you.